Hi everyone, so today we are going to look at why we can make all these ionic compounds and why the charges actually matter. So a good example of an ionic compound, so up until this point we've only looked at just the ions. You have your cation, which is the positive, your anion, which is the negative. So an ionic compound is putting those cations and anions together. And when you do that, if you use the right proportions together, that's going to equal a neutral compound. So you should never have a charge on your compound. An example of one that you might be really familiar with is sodium chloride. That's table salt. It's an ionic compound, and you are going to notice that if you write it out in the symbolic form, Na is the first one that you run into because sodium is the first one listed. Cl is your anion because it is the second one listed. And when you grab your charges from each side and drop them down like we did all during lab, you will see that it creates this ionic compound. So what's actually happened is you'll be transferring these electrons from one element to another to create those positive and negatives. So ionic bonds are really important because they're going to hold together those opposite charges, and those electrostatic forces that are holding them together are going to create these bonds. The bonds are actually very, very strong, and it takes something even stronger to break them apart. So whenever you are making something like table salt, you are going to transfer an electron from one to another. So let's see which one is which. So if you draw out your sodium, which is Na, and you draw the electron dot structure, go ahead and grab your periodic table if you need to. That's going to be your 1s2, 2s2, 2p6, 3s1. So remember, our valence electrons are the ones in the highest energy level, so that's going to be in our 3s. And it's going to probably lose this one electron because remember, we need to get to that octet. Octet means 8 electrons in your valence shell. And that seems like a lot of work to gain 7 more electrons, so instead we're going to lose just one. If you look at chlorine, which is Cl, you would get the electron configuration of 1s2, 2s2, 2p6, 3s2, 3p5. Now take a look at the valence electrons on chlorine. These valence electrons, they have a total of 7 valence electrons. So it seems like a good idea to transfer the 1 valence electron from sodium to that of chlorine. If you were to do that, you would get the following. Here's what it would look like if your sodium would donate that electron to chlorine. Again, if you lose that electron, you're going to become positive. This is our cation. And if you are negative, you become your anion. And whenever you look at the valence electrons, they complete a full octet for both of them. So if you were to underline your valence electrons for sodium, that would be your 2s2, 2p6, and in your anion chlorine, it would be in the 3s2, 3p6. Both of those are completing your octets. So that is going to form a more stable compound. Now you can use the same rationale if you were to do the electron dot structure. So remember, our electron dot structure is going to show just our valence electrons. So before we donated everything, sodium had 1 valence electron and chlorine had 7 valence electrons. So if you were to draw the electron dot structure, sodium would be Na and then 1 dot, and chlorine would have 7 dots in total. To create this idea of donating an electron, you would circle the electron from your donor and point to where it's going to go. So it would go from our Na to the Cl to create two new electron dot structures. So Na would be have no valence electrons in this diagram. It would have the positive charge, and you would have Cl with a full octet. Since it gained that one electron, you would get the negative charge. And that's shown right here as well. And this also shows you how the ions are similar to that of the noble gases of neon and argon, if you wanted to check. So some cool ones that you can look at are aluminum bromide, and that's shown in the picture on the right. And if you wanted to figure out, like, hey, how many of the valence electrons are going to be reacting with each other, you can draw that electron dot structure. So aluminum has 3 valence electrons, and bromine has only 1 valence electron. So it looks like it's just missing 1 valence electron. Sorry about that. So it looks like we're going to need to form 3 bonds with 3 bromides in order to get rid of all of our valence electrons for aluminum. So if you were to draw 3 bromides, you would be able to see exactly where each valence electron from aluminum would be donated. And that will give you your new compounds of your cation aluminum with a 3+ charge, and your 3 bromides, each having their own full octet and having that negative charge. And it actually makes a pretty cool reaction. Unfortunately, we can't do it in the lab because it is such a violent and caustic reaction. Since we can't do this in a lab, I still wanted to show you how violent of a reaction this is. So go ahead and take a look at this video. The aluminum is the silver portion in this illustration, and the bromide's at the very, very bottom. And immediately once they touch, you get this instant gigantic reaction that looks like a huge firework. So now that we understand how there is a donating of electrons and an acceptance of electrons, you can create something called a chemical formula. And that shows the number of atoms of each element in the smallest representative unit. Meaning, once you do your cross drop down, you have to do that reduce. You have to reduce your subscripts. And the reason for that is ionic compounds don't exist as individual units. Instead, they create this crystalline structure that has positive and negatively charged ions over and over and over again, repeating themselves. And that's why whenever you pour out salt, which is over here on the right, it looks like a little cube. So the chemical formula of an ionic compound refers to that ratio of the cations to the anions, and that's called the formula unit. And whenever you are creating your formula unit, you can figure out if you need to reduce, just like you do in math. So we're going to use our electron dot structures to predict the formulas of an ionic compound formed by potassium and oxygen, and then with magnesium and nitrogen as well. Let's use these electron dot structures to predict the formulas of potassium and oxygen first. So I've already written out the our electron dot structures of potassium, which is our first one, as well as oxygen, which is our second one. Now, if you were to take this one potassium valence electron and put it into oxygen, it doesn't look like oxygen will have enough. Oxygen starts out with 6 valence electrons. So if you add one more, that does not give us our 7th or our 8th electrons. It only gives us 7. So in order to counteract that problem, we just add another potassium atom in there, donate the second electron to oxygen to give us 2 potassium ions that have a plus charge, an oxygen with its full octet with a 2 minus charge. So whenever you go to write that compound, you would start out with your cation ions, which is your potassium, and however many you have, you make that your subscript. So that would be K2, and then you would write how many oxygens you have, which is just that one. So our final answer would be K2O. Now let's take a look at the second one. Right now we start out with 2 valence electrons for magnesium. Our nitrogen ion has 5 valence electrons. Okay, so let's give this a shot. Let's donate our 2 magnesium electrons to nitrogen. So you go ahead and donate that one right there. We can donate the second one all the way over here, but we don't have the right number. We only get to our 7 valence electrons for nitrogen. Okay, so let's go ahead and add one more magnesium, see how that goes. So again, magnesium has those 2 valence electrons. It can donate the one. Now that nitrogen's all set. However, what's our problem? We still have this extra electron for magnesium. Oops, sorry about that. We have this extra electron right here. So in order to counteract that problem, we have to add more nitrogens. And we're going to continue to do this addition of nitrogens and magnesiums until they both have full octets. So let's see here, we have our nitrogen. Once again, it has our 5 valence electrons. Okay, it's going to donate this extra one. But it looks like, once again, this guy, the nitrogen, has not enough valence electrons. So we have to add one more magnesium, both having those 2 valence electrons. But this time I think we're going to be okay. We're going to take this valence electron, pop it right there, and finally throw our last valence electron. So both of our nitrogens have a full octet, and all of our magnesiums have a full octet. So if we were to clean this up a little bit, we have magnesiums having 2 plus charges since we lost those 2 electrons. We have 3 of them. And we also have 2 nitrogens with a 3 minus charge, but they have a full octet. And if you were to write this as a formula, you would take your Mg's, because once again you take your cation first, so Mg's. And how many do you have? You have 1, 2, 3 of them, so that's your new subscript. And then followed by your nitrogens, and how many you have of those, which would be 2. So our overall answer would be Mg3N2. And that's taken out through our notes as well, if you need to see it a little bit better, a little bit less messy. So here are our different, it's the same steps but in a typed format, if that helps you out. And let's do one last example before we go. So we're going to do one last example of our calcium and fluorine. So if you want our calcium and fluorine, we start out with our 1 calcium that has 2 valence electrons, and we start out with our fluorine that has 7 valence electrons. So if we donate 1 valence electron to fill that octet for fluorine, we still have this extra one. So we must add another fluorine in order to figure out where that other electron's going to go. So that second electron's going to go to our second fluorine, completing its octet as well. Overall, that would give you 1 calcium with a 2 plus charge and 2 fluorines, both with full octets. But they both have a -1 charge. So if you were to start with your cation, as always, that would be Ca, and how many you have, which is 1. And then you'd write your anions, which is your fluorine, and how many you have, which is 2, for our overall answer of calcium fluoride. And that's taken through right here as well. And as always, at the end of every section, you have your key concepts and your vocab words that you should make sure that you know. All right, I'll see you next time.